So now we're going to look at our first real reaction that involves radicals, namely the radical addition to alkenes. Now, we've already seen several addition reactions of alkenes, right? So here I'm pointing out I have 2-methylpropene reacting with hydrogen halide to produce an alkyl halide. And we say that this follows Markovnikov addition because the hydrogen goes to the carbon with the most number of hydrogens. That's simply Markovnikov's rule. and yet we, through looking at the mechanism of this reaction, discover why that is the case. Namely that the alkene is a nucleophile, the hydrogen halide is an electrophile, and so the 2 pi bonds of the alkene donate to the proton and form a bond, right? And as this bond formation occurs, the hydrogen halide bond breaks, and the result is a carbocation. And of course, we're going to form the more stable carbocation, and this is the reason why Markovnikov addition occurs, because when in that formation of the more stable carbocation, the hydrogen goes to the carbon that's least substituted. Now, obviously, a halide also forms. So now we have these intermediates, the carbocation intermediate that is now electrophilic, and the halide, which is nucleophilic. And so the nucleophile attacks the carbocation, and we end up with our alkyl halide. And we see that, the hydrogen halide could be hydrochloric acid, hydrobromic acid, or hydroiodic acid in this case. Interestingly enough, historically, these reactions didn't always follow Markovnikov addition pattern. It was observed that if I took 2-methylpropene and I reacted it with HCl, I always got Markovnikov addition. So this reaction with hydrochloric acid always follows Markovnikov addition. And likewise, the addition of HI always follows Markovnikov addition. However, HBr is a different scenario. Sometimes groups would run this reaction with HBr and they'd get Markovnikov addition, and sometimes they would run it and they would get what would be designated as anti-Markovnikov addition, where the hydrogen adds to the carbon with the least number of hydrogens and the bromine is adding to that other carbon. And so the question was, why was this occurring? Well, it happens that the purity of the reagents and the solvents came to be a big factor in this. And after a lot of investigation, it was determined that what was causing this abnormal behavior, this anti-Markovnikov behavior, was actually peroxide. So remember, we talked about peroxides easily forming radicals, right? Because that oxygen-oxygen bond is relatively weak. And so when you take 2-methylpropene and you react it with HBr, in the presence of peroxides, you only get this anti-Markovnikov addition as the only product. And so this is when chemists went, oh, okay, this is very interesting. What's happening mechanistically to give us this anti-Markovnikov addition? And so obviously, we talked about peroxides being readily forming radicals, and certainly that is the case. And so when we look at a radical mechanism, we tend to look at it in various steps. And you have to understand that, if I have a peroxide, not all of the peroxide is going to dissociate into peroxy radicals. But the key is that when I have this peroxide, I only need a very small concentration of peroxide to undergo homolytic cleavage. And so in the presence of light, typically, or heat, this readily happens. Right? So I add just a little bit of energy to the system. I get a homolytic cleavage of the peroxide, and I form essentially two peroxy radicals. For every one peroxide, I get two peroxy radicals. So now what happens? Well, that peroxy radical obviously is fairly reactive. And so the second step involves the peroxy radical abstracting a hydrogen from HBr. And so we get, the typical hydrogen abstraction, where the electron from the peroxy radical combines with one electron from that HBr bond, and you create an oxygen-hydrogen bond. And then that other electron goes to the bromine. The result is you form an alcohol plus bromine radical. So now we see a bromine radical that's going to be involved in the reaction. Now, we say these two steps are what initiates the reaction, and we're going to see why that is in just a little bit, because all I need is a small amount of bromine radical, and that bromine radical in step 3 is what is going to react with my alkene. Right? So here I have an alkene, and I'm reacting it with that bromine radical. And that pi bond of the alkene is much weaker than an alkane, a sigma bond. And so that pi bond can dissociate, and we get a formation of a carbon-bromine bond, and then that second electron goes to one of the carbons. So we're creating a carbon-bromine bond on one carbon, and the other carbon becomes a radical. And the result looks like this. Right, so now I have this alkyl bromide radical, and of course we know that alkyl bromide radicals, radicals in general, are reactive, and so that radical is going to react with HBr. Now you might be saying, well, didn't I just use HBr in step 2? Yes, we did, but remember, we only used a small amount of HBr, right? You can almost think of this as one molecule of peroxy radical reacting with one molecule of HBr, where I have a whole mole of HBr present in my reaction mixture, right? So I still have a lot of HBr present. And so that radical is going to react with HBr. And again, I'm going to abstract a hydrogen from HBr, and the other electron goes to bromine. And the result is, now I'm getting my alkyl bromide, plus I'm regenerating the bromine radical. Because I'm regenerating that bromine radical, it can go in and react with another alkene to give me that alkyl bromide radical, which can react with HBr to give me more alkyl bromide plus bromine radical. And so this process repeats. Step 3 and step 4 continuously repeat. And we call this a chain reaction, right? So we call steps 3 and 4 chain propagation steps. Now the key to understanding this mechanism is it's very different than the mechanism of carbocation formation, right? So substitution and elimination reactions involve, essentially one mole of reactant reacting with another mole of reactants. Free radicals mechanisms involve essentially one molecule of radical and then a chain reaction occurs, right? So the radical initiates a chain reaction in which steps 3 and steps 4 repeat one another over and over and over until you build up a large amount of product, namely the alkyl bromide. Now, There certainly are termination steps and so a termination step is when the product is no longer a radical. So the key for steps 3 and 4 is that you're producing radicals, and those radicals are going to keep reacting and reacting. It is possible where radicals react with other radicals. And so at the end of a reaction, when you don't have very many reactants that can actually react with the radicals, they're going to then find other radicals to react with. So this process produces very insignificant quantities of these side reactants, and we tend to not worry about them very much. But just to kind of get you thinking about what could be a termination step, and I'm going to list a few possibilities. There are many. Essentially, whatever radicals are present can react with other radicals. So if I have an alkyl radical, it can react with another alkyl radical to give me an alkane. If I have a bromine radical, it can react with another bromine radical to give me a bromine molecule. If I have an alkyl bromide radical, it can react with bromine radical to give me a dibromide, right? So these are three possibilities of quite a number of possibilities. Right? So let's look at the regiochemistry, right? Obviously, this is an anti-Markovnikov addition, right? So when I react an alkene with HBr, and HBr only, then this anti-Markovnikov addition occurs. So we know that upon formation of the bromine, it's going to react with the alkene. So one electron from the pi bond goes to the bromine, and the other electron essentially has, we can think of it as having a choice of going to the carbon on the left or the carbon on the right, right? So I'm going to show both scenarios and see what kind of happens as a result of that. If the electron goes to the carbon on the left, we see that we generate this alkyl bromide radical that is a tertiary radical, right? Now, if, on the other hand, I take the alkene and react it with bromine, right? Same way, but now this time that last electron goes to the carbon on the right. The result is this, right? So bromine is going to form a bond to the carbon on the left, and then I get a primary radical. And so we talked about stability of radicals, and we see that tertiary radicals are much more stable. So the intermediate here, the tertiary radical intermediate, is going to be at a lower energy level than the primary radical intermediate, and so we can essentially control regio selectivity this way. So the more stable tertiary radical is formed over the less stable primary radical, and the latter reaction does not occur whatsoever. And so once that tertiary radical is formed, right, so here I have my tertiary alkyl bromide radical, it's then going to react with HBr, and I'm going to get hydrogen abstraction from that HBr, and so now I'm forming a hydrogen bond. And so notice I'm forming that hydrogen bond on the carbon that is the more substituted carbon instead of the less substituted. Or in other words, in terms of the Markovnikov rule, I'm actually forming a carbon-hydrogen bond on the carbon with the least number of hydrogens, and therefore we say it is anti-Markovnikov addition. Now, how does this play out in terms of synthetic purposes? Well, so now we see that we can really control the regioselectivity of a reaction. So now if I have an alkene and I treat it with HBr by itself, so I'm assuming there's no peroxides present, I know that that bromine is going to go to the more substituted carbon, because the hydrogen is going to go to the carbon with the most number of hydrogens. I'm going to generate a carbocation. Bromide is going to attack that carbocation. I get the following product, right? So one bromo, one methyl cyclohexane. However, right? So Markovnikov addition, right? If I treat the same methyl cyclohexene with HBr in the presence of peroxides, this follows an anti-Markovnikov addition, right? The bromine, so the hydrogen goes to the carbon with the least number of hydrogens. The bromine goes to the carbon with the most number of hydrogens. And I get 1-bromo, 2-methyl cyclohexane. And so this follows the anti-Markovnikov addition. Hence, the regioselectivity of this process.